Up to this point, we showed a single integral application. We only had one independent variable x and function value y. In that scenario, you can use the previous all the previous integration formulations, but there can be more than one input value. With x, there can be another input like y, which is a two-dimensional function, and these are called multiple integrals. It can be 2, 3, or 4 inputs. That's why it's called multiple integrals. And for multiple integrals, we can also use numerical integration. And it's widely used in engineering, especially two-dimensional one. For example, a general equation to compute the average of two-dimensional function is like this. The function, actually, these are the integrations, and this is the mean by the different, the ranges of these. In here, the techniques discussed in this chapter and the following chapter can be readily employed to evaluate multiple integrals. A simple example will be to take the double integral of a function over a rectangular area, iterated integrals. So what we do is basically we first take the integral of this, then another integral of the integrated function. On the right hand side, you can see a two-dimensional function actually with y and x inputs, and this is the output. That means we will have a projection of it. This is kind of the rectangle that we are integrating this and having this area, we can say, this rectangular area. So the integral in one of the dimensions is evaluated. Here, for example, with respect to y, first we evaluate the integral. The trapezoidal or Simpson's rule are applied in the first dimension, while the second dimension remains constant. So just use the function for y by using trapezoidal or Simpson's rule again, like the numerical integration. Once you integrated it, then use again the first integration result with the integration with respect to dx, for instance, the other dimension, let's say. And the numerical method, like trapezoidal or Simpson's, is applied again here to integrate the second dimension. Here we have an example application of using double integral and the numerical integration for double integral. We have an engineering example. A temperature of a rectangular heated plate is given by this function, which has x and y as inputs, and T is the temperature output. If the plate is 8 meters long and in x direction and 6 meters wide in y direction, x and y's are the plate's dimensions in x and y directions, to compute the average temperature. So we need to compute this. But of course, to be able to compute the average temperature, average means we need to take the integration of this. So it's basically average means T average, the integral of this function divided by 8 minus 0 and 6 minus 0. So we need to take the integration of this. So let's take the integration. Let's plot the function area first. Let me try to erase this. And here on the left hand side, you can see the x and y. X is actually from 0 to 8 here. Actually, this is 8, you can think. This is 4. And in y direction, this is 0, 3, and 6, basically. Why did we divide it with 4 and 3? Because we wanted to use the two-segment application of trapezoidal rule here. That's why we needed to divide it here. And first, what we need to do is we apply the trapezoidal rule along x for each y value. So here you can see 0, 40, 48. So 0, 40, here one trapezoidal, here also one trapezoidal rule, and two divisions. So it becomes this value as the integral. And for this as well, one trapezoidal rule here, one trapezoidal rule here, it gives this value to us. And here as well, one trapezoidal rule here and another one here, it gives this value to us. So we integrated in x. Now we need to integrate in y. So we will use these final results to integrate. Simply, If we integrate this, so here one trapezoidal rule and here one trapezoidal rule, which gives us 6 minus 0 because the y values are 6 and 0, and the final result is this, and this is the denominator, and denominator is the differences, so 0.8 minus 0 and 6 minus 0, which gives us, when we divide by that, it will give us the temperature, average temperature. So divide this by this one, and it's the average temperature is 53. And the true value from analytical integration, if you take the integration of this, the true value of temperature is 58.6667. And you can see that there is a difference, but it's pretty much closer. And the true error is 0.7%, 9.7%. So it's below 10%. Of course, to improve the error, you can maybe use, for instance, for this data, Simpson's rule. Simpson's 1-3 rule here, Simpson's 1-3 rule here, Simpson's 1-3 rule here. And then finally, for this Simpson's 1-3 rule in the y direction ones, and you will get maybe a better result. And here actually we show the alternative. And for these values, and by getting a Simpson's rule here as well, the result is 28116. And when we divide it by 6 times 8, the temperature is this. So we divide it by 6 times 8, and the result is this. You can see that this is actually the same as this one. So the Simpson's rule gives the exact result. And the reason why, if we ask, it's because the function is a second order polynomial. And we know that the Simpson's 1-3 rule is using a second order polynomial to predict this function actually, because it has second order and actual function is second order, so it has to give the exact result. So it's an exact representation of this because the orders are the same. And Simpson's rule actually can even give the exact result for cubic polynomial. We said that already. And here it's second order, so that's pretty straightforward that we will get the exact result. And true error is this because we have the fourth derivative. Up to 3 order of 3 we will get exact result. And that's the reason of why we are getting exact result actually. This derivative is in the fourth order for the error.